Right, so to get us started, what have I drawn an outline of up there? Just periodic table. Okay. So I sort of gave that away with what we talked about at the start too. So this is basically your outline of your periodic table. What are the giveaways that it's just not a group of boxes? Sort of jaggedy top. Okay, so why could be a factory with some fences in the front row. I love judging my drawing. It's a bad drawing of the periodic table too, to be fair. It's got no details, it's got no symbols. Okay, so, but you're right, these jaggedy things sort of are the giveaway because we know enough about the periodic table now to go, they're there for a reason. Okay, so why is there this first jaggedy bit here? What is that caused by? Or what does that signal the end of maybe, or something like that? A group, okay. So does that group go that way or does it go that way? Downwards. So we're saying that actually you could imagine a dotted line down here and this would create a thing called a group. Yeah, and not surprising, it's called group 1. And I'll use Roman numbers here, group 1 or group 1A. Do we know what the very first atom is that's there? Hydrogen. Okay. That's a bit of a weird one because it's actually a gas. Because all the other ones below it are not gases. So actually, it kind of doesn't belong there. Even though you saw that and went, oh yeah, let's start a group 1. The funny thing is, this actually belongs sitting about here. In the middle of nowhere, because it's so unique. However, we put it there for a whole lot of reasons, and we'll get to that in a moment. So what I'm going to sort of go through with you today is how we use this periodic table and our understanding of its shape basically to understand things we don't know anything about. A guy called Mendeleev, and there was another person whose name I've forgotten, I'm really sorry, who wasn't Russian, both came up with basically the layout for the periodic table at about the same time, but Mendeleev got all the kudos for it, which is why I remember his name and not the other one. But yeah, so we've got group 1. So not surprisingly, the next column down is going to be called group 2. Cool. Okay. And what we've got, sorry I forgot to put in lithium there. We've got lithium, we've got sodium, we've got potassium, and so on. And then after that, we probably don't know a lot about it, which is fine, because we generally learn the first 20 before year 12. Here, we've got beryllium, which is also a bit of a weird one, because it's not really a metal. But then it starts getting a bit more understandable. Magnesium, calcium, and again, we won't worry too much about the details. Then, does anyone know what's in this space here? Can you name some things that are in it? Tin, gold. They're metals. They're all metals. But they're a special type of metals that actually you learn about mainly next year in year 13. But there are a few select ones you need to know something about. What's really frustrating is in this group here, which is groups 3 through to 12, or 3A through to, now I've got to try and remember numbers now, through to 2B, things are a bit confusing and a bit weird. In your understanding of atomic structure, especially electron clouds, or electron shells if you want to call them that, is not good enough to understand what's happening in here. And if you want to push yourself to that level this year, great, but it's not part of the curriculum that we're doing. Alright? We generally call this area the D block or transition metals. You might hear it called the D block or the transition metals. There are what we call variable oxidation states with those things. It means that their ions can have more than one possible charge. Not for all of them, but for most of them. There are things that you will have met a lot this recently, where your iron, which will be Fe2 plus or Fe3 plus. Copper, which can be Cu plus or Cu2 plus. You've got other ones that are really funky because of the colours they are. Things like gold. Or because mercury, which is a liquid even though it's a metal. So it's got most of the funky ones in it, the really cool ones. It's also got things like tin, which I heard said before. It's got silver, copper, which is another coloured one. So you've got a whole lot of things in there that are just, done copper, whoops, that was already done. Manganese is one we meet this year quite a bit, which you probably haven't met before. Zinc is in there, even though zinc's only got a 2+ sign. So there's a whole lot of weird ones in there that we can't really use the periodic table with our current knowledge to explain why. But don't worry, you don't have to. We do have to be able to explain this one, and then the ones we're about to meet over here. So if we keep going with our groups, let's sort of, I'm just going to draw something in because it's important, and hope like heck I've got my 1, 2, 3, 4, there's 5. And I've gone way too deep with my periodic table, so I said it's a bad periodic table. That's an important line. Does anyone know what that line represents?
The gas element.
Not quite gas, but you're on the right track. Non-metals, cool. Everything on this side is a non-metal, and that's why we say, look, hydrogen really should be over here because it's a non-metal. Everything here is a non-metal. Everything here is a metal. So most things are metals. Most elements are metals, which is kind of handy because it makes it easier to understand why they become the ions they do and stuff. Okay, so here, not surprisingly, 3, well actually it's 13, but we're going to call it 3 because we're going to ignore the D block for year 12, apart from some of the special ones inside it. 3, 4, 5, 6, 7, 8. Why is 8 or 18 so important?
Noble gas.
Cool. They were the last ones to be discovered. They were not, I don't think anyway, that they were on Mendeleev's table. Why not? I sort of gave you the answer in a way, but why? So what? From what I've just said, why weren't they probably not on? Why were they probably not on Mendeleev's table?
They were just discovered.
They hadn't been discovered yet. Yeah. What makes them so hard to discover?
They don't react.
Yeah, they don't react. So we can't find them in any compounds. We have to find them as a pure substance, as an element, and because of where they are, they're gases because they exist as atoms. Okay, so that's your helium, your neon, and your argon are the main ones for this year. Krypton becomes important next year. And we should know these. I'm not going to fill them all in. But what's really interesting about it is that you can actually keep making some predictions about things. If I have a look at group... If I have a look at group 1, hydrogen becomes an ion that is H+. Lithium becomes Li+. Sodium is Na+. K is K+. So all of these can become +1 ions, and they're the only ions they can become that are stable. Any other ion you try to make will turn back into those other ones. Why?
Atoms like to be stable.
Yes, so how's losing an electron for these making them stable?
Because it gives them a full valence share.
Superb. So I can use the periodic table to make an early prediction. Once I get down past 20, the predictions get a bit loose. They don't always work. But up to 20 anyway, up to number 20, I can use this to predict what charge the ions are going to have. So the ions are going to be +1 here, +2 here. Guess what for here? Group 3 +3. This one I'm not going to fill in. This one +5, but you can't lose 5 electrons. So instead it becomes -3. So it actually picks up 3 electrons. -2, -1, and this is 0, which means that it can't form an ion that is stable. Okay. Haven't filled in this one because rather than a charge, we call it a valency, and it's got a valency of 4. Valency means how many chemical bonds, single chemical bonds, can it make and be stable. So this is carbon and silicon, are the two that you've probably met before. Has a valency of 4. 4 chemical bonds, and it will be stable. Now, this one here, the -3, even though it's got 5 valence electrons, we say it's got a valency of 3 as well. So it doesn't have to become a -3 ion. It can make 3 covalent bonds. So it can share electrons with 3 other things, or can make 3 individual sharings. So it might be, for example, sulfur and oxygen and sulfur dioxide. One of them, they share 2 pairs of electrons to make a thing called a double bond, and in the other sulfur-oxygen bond, it's just a single. So it doesn't have to be a fair sharing. It can be, for the 3, it can have 2 there and 1 there. Okay. Valency of 2, valency of 1, and valency of 0, of course, which means it can't bond at all. until you get down to xenon, and then things go fun again next year, trust me. So the periodic table tells me some really cool information. It's told me so far, oh, and by the way, I'm ignoring these two bits down here because they are what we call the F block. They're basically mainly man-made, which is the reason that we ignore them. Radioactive and or man-made, so they don't last long. So what we've actually been able to look at it is we've been able to look at, and I hope this fits on the screen in the video, if not I'll photograph this. We've been able to look at their valence electrons by where they are, which column they're in. Doesn't work in the transition metals. Really sorry, you're just going to learn those ones off by heart. We've learnt the valence electrons, therefore we've learnt the valency. Okay, and that therefore tells me whether they make ions or not, and if they do, what are those ions going to have, what charge. So my periodic table tells me a lot of information. But there's a lot more to it. I'm going to zoom in on chlorine, which I haven't put up there, so let's do it. I'm going to zoom in on chlorine, and I'm going to have a look at what its symbol would look like. And it's Cl. Probably has the word chlorine there too, I'm not going to put that. It has two numbers with it. It's probably got a 17 written nice and big on a periodic table up there. And it's probably got a number 35.45 down here. Okay, that's not a nuclide. I'll show you what a nuclide is in a minute. This is its symbol. Now symbols are done a funny way. The big number really should be at the top. This tells me quite a lot as well. The 17 is, what do we call that? Go with someone other than you, because
The atomic.
atomic number. Okay, what does the atomic number tell me about this atom? Not its ion, the atom. It tells me two things. Two things.
How many protons it has?
Perfect. So number of protons, and it tells me as an atom what else it has, because atoms are neutral.
Electrons.
Cool, number of electrons. Perfect. Okay, so I've got a lot of information from my periodic table. Not only do I have its valency, I also know how many electrons, so I can work out how they're arranged. Get to that in a minute. This number at the bottom is called the relative atomic mass, which you may not have met before. Okay, the relative atomic mass does not mean the number of protons plus the number of neutrons. Okay, it does not mean that. What it means is, what is the mass of 1 mole of these atoms? Now, mole's a big, big, big number, basically 6 times 10 to the power of 23. It's a huge number. It's the number of carbon-12 atoms in 12 grams of carbon-12. That's the way it's defined. Okay? So how does that work out? It's 35.45 grams is how much 1 mole weighs of chlorine atoms. But actually, the only things that are made up that have mass in an atom, really, that we can measure, are the protons and the neutrons. And that gives us its mass number, which is subtly different. So you might have seen symbols like this that are called nuclides. These are the two most common isotopes. They're the only two that are stable. These are the two stable isotopes of chlorine. What that means is that this chlorine atom here has got 37 things in the nucleus. This one has only got 35. I know from the 17 that 17 of those things are protons. So the other 20 are neutrons. In this one, 17 of those things are protons. The other 18 must be neutrons. This magical number here tells me which one is more abundant. The number is 35.45. Which one is it closer to? The left or the right? The right. Which means, roughly, I think it's about 75% of all chlorine atoms are of this isotope. And only about 25% of all chlorine atoms are this isotope. That's why if I had 1 mole of it, I would expect, if I add them all up, that it would weigh 35.45 grams, or have a mass of, I should say. it would be 35.45 because both isotopes were present. Mainly this one, which is why it's so close to 35, but there's going to be quite a few of these as well. Right, and I said the other cool thing that these things tell us, the number of electrons, valency, so we can look at the electron configuration. This is what I really love about the periodic table if I know how to use it very cleverly. If I have a look at the first period, which is the first line across, I hope that's showed on the video, so can you guys all see the thing there, the first period? Hydrogen and helium. How many atoms is that? Or how many elements? 2. Well, actually, how many electrons fit in the first shell? Electron shell? 2. Okay. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. How many atoms was that? Let me check on another periodic table. 8. How many electrons fit in the second shell? 8. So if I'm looking at sodium, I know that it's 2, 8, 1. Because I just work across. 2, new line, so it must be a new electron shell. 8, get to the end. Gone to a new line, start a new electron shell. 1, 2, 8, 1. So if I'm looking at chlorine, 2, 8, and then 1, 2, 3, 4, 5, 6, 7, so 2, 8, 7. My periodic table will tell me electron configurations. I don't have to learn them off by heart. I just need a periodic table, which I'm given in all of my assessments. Pretty cool thing. So, today has been about the periodic table. The groups, which are the columns, they tell you the valency or the ion charge. Okay? The symbols themselves tell you if there are isotopes. If this number is not a whole number, there are isotopes, and it tells you which one is more abundant. Okay? The number at the top, well, the atomic number tells you the number of protons, also tells you the number of electrons. And by understanding the periods, which are the rows, I can actually use that to very quickly work out an electron configuration.